Hello everyone, welcome to IV2020. In this session, I would like to introduce generative model-based data augmentation for special person classification. Automated driving had been widely discussed. With the help of the recent technology, the vehicles today are becoming more intelligent than ever before. But still, driving safety is always the top priority. Besides the passengers and the drivers, we also have to detect and protect the VRU, the vulnerable road users. The detection module designed for VRU has been improved during the last decade. In this paper, we introduce special person classification as a crucial task in the VRU detection. Here are some examples of special person images on the right-hand side. For example, the police, the construction workers, and school guards. Actually, in real-world traffic, the behavior of those special persons is structured by laws, regulations, and common understanding. The instruction from special person has higher priority than the traffic sign and the traffic lights. A human driver would take the information about the role of the person as well as the signal from this person to take adequate driving decisions. Therefore, it could be estimated that the introduction of a special person classification function into the perception module could bring extra overall benefit for the automated driving system. But the major problem arises as most of the dataset don't provide special person information. Since that there is a low probability that the data collection vehicle meets a special person on the street. On the one hand, to collect a dataset with large number of rare cases like this would take tremendous effort. On the other hand, training on extremely unbalanced dataset would normally result in lower performance despite scaling up or optimizing the classification networks. Meanwhile, in recent years, many studies have shown great interest in generative models, especially in person image synthesis. As we can see here from the image, state-of-the-art generative images are gradually becoming more realistic, and the content of the image is yet configurable. Here we show the images from VAE back in 2014, the DC gun in 2016, and DPIG in 2018. You can see that the image quality are now comparable with the real images. We believe that this could be exploited as a novel approach for data augmentation in person perception tasks. So, our target for this paper would be threefold. The first is to build up a special person classification framework using convolutional neural networks, which could categorize the person into pedestrian, policeman, road workers, and school guard. And secondly, to solve the widely existing class imbalance problem, we built a generative model for data augmentation through generating rare special persons. And third, to experiment with different data settings and backbone network so that we can demonstrate that our approach outperforms other widely used methods qualitatively and quantitatively. The generative model-based data augmentation for special person classification, in short, the GMDA. Here's the roadmap of the GMDA approach. So our method leverages generative model for special person classification. The raw dataset, which is class unbalanced, would be fed into the generative model. The generative model is built to generate the rare special person samples, which are then integrated with the raw dataset and fed into the classification model to boost the training of the classifier and thus acquires higher overall performance. In the paper, we have an in-house dataset which includes pedestrian, police, workers, and school guard. To imitate the person distribution of naturally collected dataset, which is imbalanced, we further randomly filtered out special persons instances from the original train set, which is here the train 100, and generate train 10%, train 30%, and train 50%, namely the remaining 10%, 30%, and 50% in comparison to the original volume. Here we only show the 10% version. On the left-hand side, we show the instance number difference of the train 10% and train 100%. We also can see huge performance downgrade after the dataset becoming imbalanced from the statistic on the right. We can see that the performance dropped from 96 to 97% to 91 to 92%. For the generative model, the goal of the generative model is to learn a disentangled representation of appearances and poses of the person images on bounding box level in an unpaired manner. Then synthesize the new person images conditioned on the target poses and appearances. In this paper, we use the variational U-net as our generative model. The Bardi ROI cropping and the normalization of the VU-net are also adopted. In addition, we use self-occlusion tags in the training for the pose generation so that the self-occluded part would not be presented in the final image. Such choices guarantee a more concrete and realistic pose and ROI's presentation. Our person image generation consists of two phases, the training phase and transferring phase. The process is shown in the image on the right. For the training phase, given an image X and its corresponding pose Y, the appearance Z is sampled from the X and Y. The reconstructed person image X hat is generated conditioned on the Y and Z. For the transferring phase, additionally, the target pose YC was given. The synthesized person image X hat is now generated conditioned on YC and Z. The training loss are the weighted sum of the KL losses, the content reconstruction losses, and the style reconstruction losses. Here are some examples from the motion transfer using our generative model. Those images are different appearances conditioned on different poses. The artificial sample are indeed photorealistic. Here we also show the performance with different data setting and different backbone networks. So we can see here the NOS refers to direct training without oversampling technique. The train 10% plus OS applied with oversample technique, and the train 10% plus GMDA was trained on train 10% mixed with the artificial images. The results indicate that both OS and the GMDA generally improve the classification performances against the baseline 10% NOS. But GMDA outperformed OS with a slightly larger increase in all 5 networks. On the right, we can see some example of the correct prediction on the test set. It is also worthy to mention that there are limitations in the implementing GMDA approach. The limitation becomes visible with more real data available during the training. So adding same amount of real data is always better. The generative data is not as good as the real data. And secondly, the quality of the generated images needs to be improved. The hard cases, including the large occlusion and large foreground-background overlap, is still too challenging for the GMDA. Third is that training on pure GMDA images mixed with all real pedestrian becomes problematic, since the classifiers learns the heuristic information regarding the real and fake classes instead of the interclass differences of the special duties. And finally, to the conclusion. Firstly, we introduce a special person classification and use convolutional neural networks to classify the special person. Secondly, we use generative model to generate images of rare classes. Third, we mix the generative images with the real images to build a balanced dataset. Fourth, the GMDA shows clear advantage over traditional oversampling method. And finally, we investigate the limitation of current generative model. Thank you for watching.